Hello, Darshan. I guess we'll get started in 5-10 minutes while a few others also join the session in person. So, Satvik and Darshan will start in like 5 minutes, just waiting for a few others to join. Okay, so I guess no one else is joining the session, so we can get started. Hello everyone, I'm Lakshya Saggi. Just to introduce myself, I'm the problem solving TA for the Monday 6 to 8 p.m. sessions for the NPTEL Games and Information course. And this will be our third session, and this will be somewhat more of a lighter session than the previous two because I think in this week's lectures, not a lot of things were covered, mostly mixed strategies and saddle points. So we'll have problems related to that only. And once again, I'll be expecting you, while discussing the problems, I'll be expecting that you guys have gone through the lecture videos. So we'll be focusing more on the problem solving part. I think we'll be, I think if you have gone through the lectures, today's problems will be like somewhat easier and very similar to the quiz problems which are there for this week. So yeah, you guys won't be having much trouble understanding today's problems, I hope. So I guess we can get started and I'll just share my screen and we can start discussing the problems. Also, at any point of time, as usual, if you have any doubts or like any technical issues arise, like you are not able to see the screen or my audio is not clear, feel free to type it out in chat so I can try to rectify that. Okay, I hope the screen is visible to everyone. So we can get started now. Again, as usual, we'll start with two or three very simple questions straight from the lectures, which are more kind of warm-up questions for us. I'll be expecting you guys to give the answers to these. First question is this. Let A be the payoff matrix of a zero-sum game between a row player and a column player. And now we have to select the correct options. There can be more than one option correct. Then the options are the matrix A must be an invertible matrix. The matrix A must contain a saddle point, and A must be a symmetric matrix, and none of these. Uh, what do you guys think? Uh, First of all, I hope everyone knows what the payoff matrix is. So payoff matrix is uh, just a matrix which denotes like the I comma jth entry of the matrix denotes the reward for the row player when the row player plays I and column player plays J. And since it's a zero sum game, so negative of this entry. So Aij gives us the reward for the row player and minus of Aij gives us the reward for the column player for the payoff matrix. Uh, Darshan or Satvik, would you like to answer this or just maybe try to guess the answer also? What do you think may be correct in this for this question? That the matrix A, the payoff matrix, must be an invertible matrix, must have a saddle point, it must be a symmetric matrix, or none of these. Okay, I guess no one is answering. I'll just straight away say that the answer for this is actually none of these. Like answer is like option D. And why is this the case? Because uh, this is because the matrix A can be any arbitrary matrix. So payoff matrix is any arbitrary matrix can be the payoff matrix because you take any matrix and you can say that it is a payoff matrix for a zero sum game because the matrix A will denote the rewards for the row player and minus of this will contain the rewards for the column player. So A does not have any special property. A can be any arbitrary matrix. So it need not be that it is always invertible. A can be a non-invertible matrix. Similarly, uh, this has also been discussed in the lectures that so in the lectures also there was an example of a matrix which did not have a saddle point. Like there are zero sum games where there is not a like deterministic saddle point. There does not exist a deterministic saddle point. And similarly, A must be a symmetric matrix. This is also not true. You can just take any matrix and you can just call that a payoff matrix, and it need not symmetric matrix. A can be an arbitrary matrix, and so it need not. A can be any arbitrary matrix. It need not be invertible or symmetric. Also, as discussed in the lectures, there exists matrices which do not have a saddle point. And for these matrices, we say that the zero sum game for these matrices does not have a solution. For these matrices, the zero sum games like do not have a solution. Yeah, this is essentially saying that the deterministic Nash equilibrium does not exist for games where there are no saddle points. Yeah. Then again, if there are any doubts or any questions, feel free to ask in chat. Otherwise, I'll just have to assume that everything is clear to everyone. All right. Then the second question is again consider a two-player zero-sum game. Suppose A, comma B and C, comma D are two saddle point strategies. Then A, comma D and C, comma B are also saddle point strategies. Is this statement true or false? Okay, so Satvik is saying that the second is true. So good job, Satvik. This has also been discussed in the lectures that this is true as discussed in the lectures. What does this statement essentially say? Suppose we have two saddle point strategies. One strategy corresponds to that uh, the row player playing A and column player playing B. So first strategy is A comma B, the pair of strategies, and the second pair of strategies is C comma D. Then what this essentially says is if we are given these two as saddle points, then we can basically if the column player chooses to play any of these two strategies, if the column player suppose chooses to play either of these B or D, and row player chooses any of A or C, then all of these possible four choices. So call the row player has two choices here like A and C, and column player has two choices B and D. Any of these possible pairing will be a saddle point then. If A comma B and C comma D are saddle points. What this means is A comma B will be a saddle point, A comma D will be a saddle point, and C comma B will be a saddle point, and C comma D will be a saddle point. So A comma D is a saddle point also, and C comma B is also a saddle point. Essentially, this is, and that's why like this statement is true. And just uh, just to so as a reminder, what do you think about the values? The payoff for let's say the player A, let's say about the suppose I'm talking about the row player. What do you guys think? The payoff for the row player in this A comma B saddle point and C comma D saddle point, will it necessarily be equal or can it be different? If the two players have playing like this A comma B, and in second instance the players are playing C comma D, in both of these instances the row player will have some payoffs, right? Here there will be some payoff and here there will be some payoff. Will those payoffs be equal? Yes, good job, Satvik. Satvik is saying that the payoffs will be the same. This was also discussed in the lectures that the payoff for at all saddle point strategies are equal. Maybe just mention this. I'll just mention this as a note. Also, the payoff received by row player will be equal for all the Saddle point strategies. Exposed. Why I'm just reiterating these kinds of points because these are kind of very important properties, which definitely come to use a lot when we are uh, doing stuff over zero sum games. Like these properties of saddle points and like yeah, the valuations of players on saddle points. So yeah, now maybe we can go to the third question. Third question is again bit out of lectures. So Aij be the let Aij be the element of the at the ith row and jth column of a matrix A. So Aij is just the I comma jth entry of the matrix A. Then the minimum over all possible i's, the maximum over all possible j's, Aij is greater than equal to. So so what does the left hand side say? Yeah, Satvik, good job. Satvik is saying in the chat that the answer is true. And yeah, this has also been discussed in the lectures that the answer is true as discussed in the lecture. Just to reiterate, what does this property mean? So let's look at this side first of all. What does this mean? This says let's look at the inner thing first. It says that the Aij over all possible j's. What we are doing is suppose we have a fixed I, and what is I? I is basically the row. So suppose we have a fixed row, and then we are taking the maximum entry out of that fixed row. So we are choosing a column such that the we get the maximum entry out of out of that fixed row. And now what we want is so for every value of I, we will obtain like some maximum entry. If there are like m rows and n columns, we'll have something like n entries here, and out of those we take the minimum. We take the minimum out of all these, and this is what this left hand side says. So basically, what does the left hand side say? That uh, take every row, take the maximum value in every row, and over all these values which you get, just take the minimum value. Whereas the right side says that you fix any column. So first you take any column, and then out of in that column, take the minimum value. Take the minimum value of the entries in that column, and out of all these minimum possible, like for every column, you will obtain one minimum value. And so out of all these minimum values for all these possible columns, just take the maximum. And this was shown in the lectures that this min max Aij is greater than equal to max over j min over Aij. Yes. This is somewhat of a warm up as this was discussed in the lectures also. So let's just try to tweak the question a bit. Suppose I had this kind of inequality here, right? That what I'm here doing is I'm taking the minimum over I, maximum over j, and I'm writing this as Aij. And here I'm taking the maximum over j, minimum over I, and I'm writing it Aij. What if I just like it's not related to the zero sum games, but in general, I think we should be able to identify what changes in the matrix if we just change something. Yeah. Suppose I just change the indices here. Here I was taking maximum over j and minimum over I on the right hand side. Suppose I swap the indices. What I now do instead is I take the maximum over I and minimum over j on the right hand side. Is this true or false? So is this updated question, this identity where you are taking the min over I, max over j, Aij, is this greater than equal to max over I, min over j, Aij or not? Think about it for a minute, guys. I think uh, like thinking out these kinds of questions gives us intuition about matrices and will be a lot helpful when we are deeper into the course. So these kinds of things. So Satvik Darshan, this has not been discussed in the lectures, but I would like you guys to think about it. Just whatever comes to your mind. If there comes any reasoning for why this is true, then Maybe type it out in chat. If this is you think this is false, just type it out in that chat. Think about it for like 2-3 minutes, or like at least 2-3 minutes. Will this kind of say? And like I hope, first of all, like I hope you guys see that these two quantities are different. Like max over j, min over I is different from taking max over I and min over j. Like this is not the same. Like if you think that swapping indices does not matter, like it will matter. Just try to draw out some examples and you will see. But what do you guys think? Will this be true or will this be false? So try to think about it for like 2-3 minutes. I'll be muting myself. I'll just go get some water in the meantime. Okay, so Darshan and Satvik both have answered that this should be false. So yes, I think that's the correct answer, guys. So good job, but maybe I will try to provide some reasoning also. Like let's try to reason about this. This is the. And like if this is false, then essentially we are saying that there will exist matrices. Like we need to show that this is false also, right? Just saying that this is false does not convince me that this is false. So we need to give an example of a matrix where this kind of inequality does not hold. And what's an example of a matrix where this won't hold? Maybe I'll try to uh, write down the matrix also. So so consider this kind of a matrix. How do I insert a matrix now? So I don't need this to be this much in size. Reduce its size. Yeah. So consider the matrix like suppose. So what are we doing? Like let's just first of all maybe understand what's this saying. So we are saying first we take a row in the left hand side and take the maximum value out of that row, and like all of over all these rows as we discussed, we take the minimum. Here also we are selecting the row first, but now we are taking the minimum value over that row, and then we are taking the maximum out of the all minimum possible values. So in both cases we are selecting the rows, and in one case we are selecting the maximum value from that rows, and in second case we are selecting the minimum value, and in the end we are taking min in the first case and max in the second case. So maybe there will be examples where this kind of inequality will fail to hold. Suppose this is my matrix. So guys, if this is my matrix, suppose that the first row has very large entries and second row has very small entries, then in this matrix, what will be the value for this? The min, this value, the minimum over I, maximum over j, aij. What will the value for this in this matrix, guys? So what will be the left-hand side here? Like you can take row by two. Okay. So Satvik is saying that the answer is two. So good job, Satvik. So here you can see that first we have to select a row and then select the maximum out. So let's consider the first row and then the second row. So in the first row, we have the maximum value. We take the maximum value out of the first row. It is 1000. And in the second row, the maximum value is 2. So we have for I equals to 1, the maximum is 1000, the value is 1000, and for I equals to 2, the value is 2. And for from these two rows, we have to take the minimum. So between 1000 and 2, 2 is actually the minimum. So that's why the min max over ij, maybe I should just copy this. Yeah. Here, min max over ij is actually equal to 2. Whereas what will be the value of max min aij here? Like first we select the row and then out of in the first row we take the minimum value. The minimum value here is 500. In the second row, the minimum value is 1. So we have the two entries as 500 and second entry as 1. And then, but we have to take the maximum instead. So out of these two, we have to take the maximum. So, and between 500 and 1, 500 is greater. So what we get is in this matrix, the min max was 2. Okay, sorry for this, guys. Yeah. In this matrix, min max was 2, but max min is 500. So the inequality fails to hold. Okay, I hope you guys get this. And now maybe just let's try to think about it a more. So we know that this inequality fails to hold. Like we have shown an example that for this inequality, in this kind of case, we have an example where this side is greater than equal to this side. But the second question now can be, will this always be greater than equal to this? So now the second question can arise. Like I hope you guys see why I'm trying to do all of this because like it helps us build more intuition into stuff and understand the matrices a bit more. Can we say that? So we know that this is definitely false, but is this true? Like if we replace it by a less than equal to sign, now is this statement true or false? Like we know that it is not always the case that this inequality holds, but it does not mean that if this fails to hold, then this always holds, right? We should still think about it if this inequality holds or not overall matrices. So what do you guys think? Like, will this inequality hold? The min over I max over j aij is less than equal to max over I min over aij. Just think about it for a minute or two also. Like, we know that this inequality is definitely incorrect, but does this mean that is this inequality correct? What do you guys think? Okay, so Darshan is saying that this is true, that this will always hold true. Okay. Uh, any opinions from your side, Satvik? What do you think, Satvika? Will this be true or false? Okay. So Satvik says that he does not think that there is a relationship between the two terms. So yeah, actually, so Darshan, I think this statement will also be false. Like we can draw an example where like even this statement will fail to hold, and I can give you an example also. So suppose this is also false. Consider the matrix. So consider this matrix like okay. Maybe I should put the whole question on the next page for that. Yeah. Uh, Now let's say I change the matrix and I have its entries as something like this. 1 and 2 and 1 and 2. So this is the matrix. Just like both the rows are the same. And now what can we say about this thing? The min max Aij. In the first row, the maximum value will be 2. In the second row, also the maximum value will be 2. So when you take the minimum of this, you will still get a 2. Right? So this term will be 2 for this matrix. Whereas this term, here we take in the first row, we take the minimum, it will be 1. In the second row, we take the minimum, which will be 1. And then we take the maximum out of these two ones, which will be 1. So this value was 2, but this value will be 1. So maybe I should just write it down here. So yeah, here min max is actually 2, but max min is 1. Hence, this inequality also fails to hold. So exactly so exactly as Satvik said that one may try to compare these two values, the min max and max min when I and j's are these in this the first and the second. But one may try to say they are greater than equal to, but then you have an example where this is not true. And the second example is all, and we also have an example where the less than equal to relation is also untrue. So yeah. So exactly like this min max aij and max min aij, if in both of these we are taking like the first index as I and the second as j, these are not related. The only relation comes when you take like max over j and min over I here. This is an important point to note because like this is a subtle point also because this kind of question can get asked this kind of inequality has already been discussed in the lectures, but then in the exam someone might ask you that, oh, but what if I just think of it as I and j's, and then what happens? So yeah, so, good job guys. Now maybe we can move on to the next question. Uh, so so now for questions 4 and 5, this is a common data. Uh, okay, so I see. Okay, no one. So consider a two-player zero-sum game over the unit square. So we are given the unit square, and we have a two-player zero-sum game. And I hope everyone knows what does a unit square mean. This just means that like the x coordinate can vary from 0 to 1 and y coordinate can vary from 0 to 1. So it's a square which has both the sides as like all the sides of length 1. So consider two players zero sum game over the unit square where the row players strategy set is from 0 to 1. The x coordinate can vary from 0 to 1. And the column player strategy set is y, which is from 0 to 1. So both these players have some, both these players will put out a number between 0 to 1. And yeah, and so the first uh, the fourth question says that the row player wants to minimize the cost given by this value. So we also have this cost function given to us. So if the row player, what this means is that if the row player plays X and the column player plays Y, then what we get is the cost for the row player is 1 plus 4. The cost incurred for the row player is 1 plus 4x plus y minus 5xy. So we have that the row player's cost is given by this value when we are at when the row player plays X and column player plays Y. And we are also given that this is a zero sum game. So for a given X comma Y pair, what will be the cost for the column player? Uh, would any of you like to just mention? It's a very short thing which I just asked. So if this is the payoff for the row player on this X comma Y strategy profile, then what will be the payoff for the column player on this X comma Y strategy profile? Like if you say CXY is the cost of the row player and it's a zero sum game, then what will be the cost for the column player? Yeah, exactly, Satvik. So it will be minus of CXY because it's a zero sum game. So if a row player has a payoff of CXY, then column player's payoff should be minus of CXY because it is a zero sum game given to us. Okay, so I see someone else has so Harshit has also joined the chat. So hello, Harshit. So we are right now. So just maybe I can just recapitulate what we have all covered. So we were discussing this week since we there was mostly lectures around saddle points and mixed strategies and everything. So we have discussed question and zero sum games. So we have till now discussed question related to that only. One of the questions was about the properties of a payoff matrix. And so maybe you can view these in the recording later and these notes will also be uploaded. But just to give a recap of what all we have covered. So first, we discussed something about the payoff matrices, and then there was a question about saddle points that if there are multiple saddle points in a zero sum game, then all of these saddle points have the equal values, and yeah, if A, B, and C, D are two saddle points strategies, then A, D, and B, C will all C, B will also be saddle point strategies. So, and then there was this third question which we just discussed, which was just some properties of the payoff matrix, like or like basically any matrix that this property has already been discussed in the lectures, that the taking the minimum over all the rows, the maximum over all the columns, Aij is always greater than equal to taking maximum over all the columns and minimum over all the rows and Aij. So this we know was discussed in the lectures, and then we were just trying out different variants whether we can write out this similar inequalities if we reverse the indices also. Like if I write here instead of j, I write I, and here I write j, like min max ij, and here also I write max min of ij. And can we have some relation between them? And I just gave some examples where like it is not possible to uh, give any relation between these two quantities. So as a recap, like only this all has been discussed till now. And now we are at the fourth question, which is again about zero sum games and like finding the saddle point, or let's say the value of the game if it exists. So we are given that the row player's cost is given by cxy equal to 1 plus 4x plus y minus 5xy, and both row players and column players play values between 0 and 1, like any number between 0 and 1 they can play, let's assume. And now we want to find the value of the game or mention if it does not exist. So yeah. And how do we find the value of the game? We say that essentially the value of the game exists only if there exists a saddle point, right? Like this was discussed in the lectures also. Like if there is a saddle point, then only the game has a fixed value, and like the value of that game then is equal to the value at that saddle point, right? So what we want here is to maybe find out a saddle point, like if the saddle point even exists. Okay, so let's go here. Let's try to do this. So what we have is a cxy is 1 plus 4x plus y minus 5xy for the row player. So what we'll essentially be doing is, as discussed in the lectures, like how did we introduce the notion of saddle points, or why does these min-max terms come for us? So what the row player wants is to choose a row such that its cost is some minimized, right? But column player also wants to minimize its cost. So column player will then choose a column so that his cost is minimized, which means row player's cost is maximized. So whatever row the row player chooses, column player will choose a column so that this thing is maximized. And this is how we get this min-max Aij term. And now we want to find out like what I will this minimum occur at. So what X value will the row player choose so that this min-max value will be the greatest, will be the smallest. Okay, so suppose the row player plays. So what we need to find out is essentially what was discussed in the lectures as the security level. So we will find the security levels of row player and the column player, and see if a saddle point exists. If it exists, then so this will be a high level approach, that the value of the game will be equal to the value at the saddle point, and if it does not exist, then the value of the game also does not exist. So now what we try to see is we see the security levels of row player and column player and see like in these, do we have a saddle point or we not have a saddle point, right? Okay, so Satvik has I see in the chat that Satvik has already answered in the for for the fourth and fifth questions. Like for the fourth question, Satvik has written that the value of the game does not exist since there is no saddle point. And for the fifth question, Satvik has written that value of the game is 4. So Satvik, would you like to type in chat like write in chat like why would the game does not have a saddle point in the fourth question? Uh, I think what Satvik has answered is correct, but I'm just curious, Satvik, how did you, what procedures did you follow to arrive at this answer? Uh, why will the saddle point not exist in the fourth question? So, Satvik, are you typing something in the chat or no? Okay, Satvik says that the saddle point exists because the security levels don't match. Yeah, that I understand, but like, uh, what procedure did you follow to like? Okay, maybe I'll just write it down here only. That why will the security like? We need to find the security levels first to say that security levels don't match, right? But what are the security levels for X and Y player? That's what I was interested in. Like, how did you find the security levels for the X and Y players? So how did I think about this was, suppose the role player plays X, then essentially uh, the payoff for the row player is something like this, the 1 plus 4x. And maybe I can take the y out of these two terms common. So it will be 1 plus 4x plus y times 1 minus 5x, right? So this is the cost for the row player. This is the cost incurred by the row player. And now what the row player wants is, okay. So if the row player has played X, then the cost incurred by the row player is this. And like when the row player plays X and the column player now will also play Y. So what we want is something like this, the min max over. Okay, maybe I should try finding the security level for the row player. And what does this mean? Finding out security level for the row player. This just means that finding out this kind of a term. That is min over all possible X values, max over all possible Y values, the cos CXY. This is what I want to find for the row player, right? So first of all, row player, if row player plays X and the column player plays Y, we have this value. And now this Y will be chosen so that this quantity is maximized, right? And note that there will actually be two cases. So if this quantity, this 1 minus 5x, if this quantity is negative, suppose this is negative, so y has a negative coefficient attached to it. Then what should be the value of y so that all of this quantity is, okay, maybe I should just write it. So we divide this into two cases. And what are the cases? So case one is something like 1 minus 5x is less than equal to 0. So essentially 1 minus 5, this 1 minus 5x quantity is negative. And case 2 would be 1 minus 5x is positive actually. Maybe I'll move the whole question downward so that we don't have the space there. Yeah. Right. So what do you guys think the column player will choose if this is the case? Like we have this quantity c of x comma y is 1 plus 4x plus y times 1 minus 5x. Okay, Harshit is saying that can't we use partial derivative with respect to x first and then with respect to y to get min and max values? Uh, yeah, Harshit, it essentially corresponds to taking the partial derivative, but uh, I did not want to discuss it that way right now because we are just like we have just started with these concepts. So, but yeah, like for more complex functions, you will need to verify using partial derivatives. But also note that one more thing I wanted to point out, like even if you do it using partial derivatives, like with partial derivatives, you will get a solution, right? But you will still have to verify if it is a saddle point or is it not a saddle point. Because if you solve for this fourth question using partial derivatives, I believe you will arrive at some kind of a solution. But I don't think that solution is actually a saddle point. Uh, like uh, like as you say, like suppose you're finding a minima or maxima in general, like you can use a derivative and put it to 0 and find out the minimum and maximum, local minimum and local maximum of the functions, right? But it does not always mean that the local minima will also be the global minima or something like that. So here also, like you will find some saddle point, you will find some points on solving this partial derivative equations, but that will not guarantee uh, that the solution you obtain is essentially a saddle point. You will need to check some more things. And maybe like I think this kind of things will be covered in the upcoming lectures, but since it these have not been discussed yet, so I'll try to take the basic like definition based approach for now. Okay, so Satvik, did you also use partial derivatives for finding out these? Maybe you can type in chat. Just I'm just curious while I try answer this question. So suppose the case one was 1 minus 5x is less than equal to 0. So in this case, if y wants to maximize this quantity, this 1 plus 4x plus y times 1 minus 5x. Okay, so Satvik just calculated payoffs. That's good, Satvik. Good job. And like for calculating payoffs, you would have used these kinds of ideas only, what I'm discussing, right? Like making cases and seeing like what will be the better. Okay, cool, Satvik. Good job. So let's just see here. So in this case, if 1 minus 5x is less than equal to 0, what do you think will y choose in this case? Like if if this quantity is negative and y wants to like maximize of this whole term, right? We have to take like min over max over all y. Like if for a fixed x, we have to take the y such that this quantity is maximized. If this the coefficient of y is negative, then when will this whole quantity be maximized? Anyone would like to answer in chat? Like I have to maximize this whole quantity when this coefficient of y is negative. So what y should I choose? And y can only range from 0 to 1 as we were given initially in the question. Okay, exactly. So Okay, Harshit is saying that the answer should be y equals to 1. Do you guys think is that right? So Harshita, I think y will be 1 in the second case when the coefficient is positive. Because what we want to do is we want to maximize this quantity. And if this 1 minus 5x is negative, let's say it is minus half, then you would want the y to be as small as possible for the whole quantity to be as large as possible. Like if y, suppose like 1 plus 4x comes out to be something like let's say suppose x was equal to 1 here. Like suppose x was equal to 1. Then this whole quantity comes out to be 5. And then this is y times 1 minus 5, which is like minus 4. So we have something like 5 minus 4y. And now for this to be maximum, you need to take y equals to 0 so that you get the quantity as 5. If you take y equal to 1, then you will get it as 1. Like 5 minus 4 will be 1. Yeah, so good job, Harshit. So as you are writing, like y will be 0 for the case 1. So yeah. In this case, it can be seen. Okay. It can be seen that cxy is maximized if phi equals to 0. And yeah. So, and here, like, so the pay of cxy essentially boils down. So the payoff for the row player here is equals to c of x comma 0, and which will be equal to 1 plus 4x, right? But note that now what the row player will want is, so now we get that in this case, while we are still in this case, uh, like I'm still discussing case 1 only. So what we get in this case is the payoff for the row player will actually be equal to 1 plus 4x. And now row player, what does the row player want? The row player wants to now minimize this quantity over all x, right? But so what we have is now we want to minimize this quantity, but we have another constraint that 1 minus 5x should be less than equal to 0. So note that if we want to minimize this quantity 1 plus 4x, so what we want essentially is x should be as small as possible here, right? But what's the smallest possible value which we can have for this case? The smallest possible value here will be when like we have that 1 is less than equal to 5x from here. So the smallest possible value for x will be 1 by 5 here. So, so since x is greater than equal to 1 by 5 in this case, we get that uh, the value, the point, basically 1 by 5 comma 0 will be chosen in this case. And so what's the value of this value? So we just plug in like 1 by 5 and 0, and which will come out to be like 1 plus 4x. So it will be 1 plus 4 by 5, which will be something like 9 by 5. Okay. But note that we are not done yet. So we said that if the row player chooses an x such that 1 minus 5x is less than equal to 0, then the minimum that the row player can go to is 9 by 5. So row player wants to minimize, right? He has the control over the x values. So if he chooses this x, as if he chooses the x such that x is greater than equal to 1 by 5, then this will be the best possible which the role player can go to. This is the smallest possible value that the role player can go to. But role player still has a choice of taking some other x also, right? X such that 1 minus 5x is greater than 0. Essentially, which means that x is less than 1 by 5. So in those cases, actually, like as Harshit also typed in chat, we can see that in this case too, this 1 minus 5x will be positive. And if it is positive and the column player wants to maximize the value cxy, so in this case, column player will choose a value y equals to 1. Right? So here what we'll get is here cxy is maximized with respect to y. Okay, maybe I should mention that. Maximized with respect to y if y equals 1. So if y equals to 1, this will be maximized. So the maybe I'm just copying this and I'll just payoff for the row player will be c of x comma 1, which will be equal to 1 plus 4x plus 1 times 1 minus 5x. So plus 1 minus 5x. And what will this come out to be? It will be 2 minus x. Right? And now the row player wants to choose a x such that this quantity is kind of minimized. So row player will want to choose an x which is as large as possible, so that this quantity whole of this becomes as small as possible. But what's the largest that the row player can go to? The largest that the row player can go to is something like very like you can say it is exactly equal to 1 by 5, but yeah. So the largest that the row player can go to is somewhat of the 1 by 5 value, because 1 minus 5x is 1 is greater than 5x, so x is actually less than 1 by 5. You can essentially say that x is like the maximum value that x can achieve in this case is 1 by 5. So the maximum value here will be maybe I should just say that x is less than equal to 1 by 5. Maybe we can just take these cases because equal to 0 case actually will be common in both of these. Like you can take equal to 0 here or equal to 0 here. It won't matter much. Since x is less than equal to 1 by 5 in this case, we get that the point 1 by 5 comma 1 will be chosen in this case, right? And what will we get here then? So we get c of 1 by 5 comma 1. And what will this come out to be? This will come out to be uh, 2 minus of 1 by 5, which will again come out to be 9 by 5 for us. So yeah. So luckily for us, like actually this was a continuous function. So like it did not have any breaks. That's why actually for both of those cases, the optimal value came out to be 9 by 5. But there can actually be discontinuous functions where you will have to. So yeah, one more thing, Ashit, like that's why also I would have avoided partial derivative sometimes, because here we are given that the payoff function is somewhat of a continuous and derivative. But sometimes if the function given to us, if it is not like differentiable or like not continuous, then you'll need these kind of basic definitions to find out the final answers. So yeah, so knowing how to do it in the like from basic definitions is also important in my opinion. So essentially, uh, basically the value for the row player is actually equal to 9 by 5, and like for row player it doesn't matter, like yeah, so row player will like to play the value 1 by 5, and yeah, whatever column player plays like 0 or a 1, everything is fine by the role player, right? Okay. And now, so this is what we did for the row player, right? And now we'll need to do same kind of things for the column player also. So till now we have only found out the security level for the row player. And now we'll try to do it for the column player. And so for column player, what we want is we want the max. We want this to be the min over x, and we here want to be it to be the max over phi, right? And just cxy. This is for the column player, right? And now we want to do this kind of a thing. And now we'll have to see this with respect to the column player, what the column player is playing. So I'm just copying the template and then just change the relevant values. So suppose the column player plays y. Earlier we tried to write everything in terms of x, but now uh, I'll prefer to write it in terms of y, because now column player is going first and then the row player will be playing, right? So if column player picks something like y, then I can write the expression as something like this. Uh, and then what the row player would like to do is kind of minimize this expression, right? But we don't get much insight. Like it's better to, what I'm saying is maybe it's better for us to write it in this manner. Like for the row player, we wrote it in this manner, like we took out the x and we took out y as common, so that we can get a bit more insights onto like what the column player would like to play here. Similarly, we like to get insight into what the row player would like to play. So I like to rearrange this expression and write it instead like this. Like this was the original expression given to us, 1 plus 4x plus y minus 5xy. So what I'll do is I'll try to write that 1 plus y. Maybe I'll just remove this y from here, plus x times 4 minus 5. So this is also the same expression. This time I've just took out the x as common. So nice job, Harshit. So Harshit has already like made things easy for me, and he has already written down the case 1 and case 2 in the charts. Thanks for that, Harshit. So yeah, this is the what we'll be having as 1 plus y plus x times 4 minus 5y. And again, we divide into two cases like we did earlier. What we want is we want to see like, so now we want to see for a given y, what will the row player choose as the x, so that this expression is minimized. So again, we'll have two cases. One case will be when 4 minus 5y is less than equal to 0. And second case will be when 4 minus 5y is greater than equal to 0. Because in both of these cases, like one times it will be negative and one time this term will be positive. And so x can change. It's like x will likely be changing with respect to both these values. So here it can be seen if 4 minus 5 as this term is negative. So it can be seen that this whole term we want to minimize now. We don't want it to maximize. We want to minimize it. So it's minimized with respect to x. We want to minimize it with respect to x. If what's the value of x if we want to minimize it? If this quantity already is negative and we want this whole expression to be as small as possible, we'll want to give x a larger value, right? So that this whole quantity becomes very small. So we'll do it when x equals to 1. So x has a choice from 0 to 1. So it will be minimized with respect to x if x equals to 1. So it will be equal to, the payoff will be equal to c of 1 comma y. And what's the value of c of 1 comma y? It will be 1 plus y plus 1 times 4 minus 5y, which will be just 4 minus 5y. So I hope everyone is able to follow. And this will be just equal to 5 minus 4y, right? And now what we'll want is this player, the y player, actually wants to maximize this whole value. So he'll want to choose as small as y as possible. So small as y possible, the player will try to choose. But note that we have a restriction that 4 minus 5y is greater than or equal to 0. So y has a value of 4 by 5 at least, right? So y is actually greater than or equal to 4 by 5 in this case. So what we'll get is the point 1 comma 4 by 5 will be chosen, right? And what will the value then? So C of 1 comma 4 by 5 will actually be equal to so this expression was actually 5 minus 4y. So if you put y equal to 4 by 5, you will get something like 5 minus 16 by 5. So it will be something like 9 by 5, I believe. Right? Okay, so Harshit is saying case 1 is y is 4 by 5, but x is 0. Hmm. Why? So with respect to x, Harshit, we want to minimize the thing, right? And if 4 minus 5y is less than or equal to 0, then this quantity is negative. The coefficient of x is negative, right? But if the coefficient of x is negative, then this quantity will be minimized when x is as large. So we'll have that c of 1 comma 4 by 5 will actually be equal to 9 by 5 here. And but in the case when 4 minus 5y is greater than or equal to 0, here we'll want that maybe, yeah, I'll just copy this and I will try to change the values. So here it is minimized with respect to x. So 4 minus 5y is coefficient if it is positive, and we want to minimize it with respect to x, then we'll need to make x as small as possible, right? So x will be 0 in this case. And in this case, the payoff for the player will be c of 0 comma y, which will be something like 1 plus y. And but in this case, so in this case, what we'll want is if we want to maximize over the whole y, uh, then we want y to be as large as possible. But note that y is bounded by something like a 4 by 5 here. So y can't be larger than this. So exactly at the point 4 by 5, we'll be having the maximum, and the x is actually 0 here, and y is actually equal to 4 by 5. And in this case, the 0 comma 4 by 5 will be chosen. And you can see that its value will come out to be 9 by 5 also. Okay. So we get that we actually get that the min max over cxy and max min over cxy uh, is equal, right, guys? So so we actually get that the max min value over cxy and min max value over cxy is actually equal in this case, in this problem, right? So if these are equal, what do we say? Uh, am I missing? Did I do something incorrect here? Because s- so will the value of the game exist in this case? Because I think so Satvik, you told that the value does not exist, right? But what was the reasoning behind the value not existing in this game? So I see that like for this max min value is also 9 by 5 and this min max value we also arrived at was 9 by 5, right? So aren't these values equal? And so like, shouldn't this game have this saddle point and like so this kind of thing will be the saddle point that uh y is 1 by 5 and x is something like a 4 by 5. Okay, sorry, y is something like a 4 by 5 and x is 1 by 5. So I- so in my opinion, I think this game will indeed have a value of 9. So since both of these things are matching, this 9 by 5, this 9 by 5, and like there will be a point at which these two actually match. So like the point 1 by 5 comma 4 by 5 will be a point where the value will be this and yeah. Okay, so okay, so Satvik is saying that the strategy set of row and column player are only limited to two choices, 0 and 1. Oh, okay, guys. Okay, I think there's been a confusion. So this is a game over the unit square, like x is 0. So this is not a set symbol. Like the x cannot just choose like a two entry 0 or 1, and y is choosing like a 0 or 1. Like these are not two values. So this closed interval denotes like the set of all possible real values between 0 and 1. So this is how you represent all the real values between 0 and 1. Like so like x and y are actually infinite sets. So okay, I see why Satvik answered that this game like does not have a saddle point. Satvik, this is not a like discrete game. Like it's not just that x can take two values and y can take two values. Otherwise, that the question would have been, I think, very easier. Like I had to do all of these kinds of things because this was indeed yeah, because this was indeed a continuous set. So in this case, like actually we will have the game's value as 9 by 5. So since maybe I just copy this, since min over max over this is actually equal to max over min over this. So row players and column players payoff are equal and it is actually equal to 9 by 5. This means that the value of the game is indeed equal to 9 by 5. So 9 by 5 will be the answer here. So I hope this makes sense, guys. So if this symbol instead was something like this, if it was like this, then this denotes a set containing 0 and 1 values. But this symbol actually denotes the set of all possible real numbers between 0 and 1. Okay, okay. So here, actually we get that the answer comes out to be 9 by 5. Also, like since this function had some special properties that it was differentiable and continuous, so actually, like Harshit also said that you can use partial derivative to arrive at this kind of values also. So you take partial derivative with respect to x and put it to zero. You take partial derivative with respect to y, you take it, you put it to zero, and you will get some values, and this will actually be the saddle point which you obtain. So I'll just try to do this orally. Uh, I hope everyone knows what partial derivatives are. So if we take partial derivative with respect to x, it will come out to, so this one will be zero. So this derivative will be, its derivative will be 4 y. So we are taking with respect to x, so this term will be 0, and this will come out to be 5y. So this will become, when taken, if we put partial derivative with respect to x equal to 0, this will become 4 minus 5y is equal to 0. So we'll get y equals to 4 by 5. And similarly, if we take partial derivative with respect to y, what we'll get is all of these terms will vanish and this will be 1. So 1 minus 5x will be 0. So we'll get x equals to 1 by 5. So we'll get the point as 1 by 5 comma 4 by 5. And this is the point which we were getting here also. First, we were seeing that the row player will play 1 by 5. And we also saw that the column player will play 4 by 5. So yeah, actually, using partial derivative also, you come at this solution much faster. So yeah, so 1 by 5 comma 4 by 5 will also be the value, like point obtained using partial derivatives. But why I avoided that was uh, like you can do it by yourself also, partial derivatives, like you obtain the answer very fast, but like we need to know the basic definitions first, like how all these things are coming before going to like faster techniques. Because suppose in a function, like there is some function which involves modulus or something where partial derivatives don't exist, then you will have to go back to these basic definitions to do anything. And that's why I think this thing also we should also know about the partial derivatives because they help us answer faster, but we should also know about these approaches because these are actually the indeed correct approaches. And yeah, you can never go wrong with these. Okay, then. So we have a similar question again. In this question, we have that the cost for the row player is given by 4 plus 2y minus 4xy. And now we have to find the value of the game or mention if it does not exist. So I don't want to go through all of this again since we have seen this approach already. Uh, uh, Rather, I would like you guys to just do this using, maybe you can do this one using partial derivatives. Like for this kind of function, partial derivatives will work to find the saddle point. So can someone quickly uh, put the partial derivative with respect to x and x0 and y as 0 and find out the values of x and y? Like I can also do it orally, but I'll prefer if any of you answer this. So like basically what will be the value of the game for these guys? Feel free to answer it using partial derivatives. Okay, so Harshit has written with respect to it. So what will be the final answer which you get? Like, just give me the final answer, guys. Harshit, like, what will be the point at which uh, the like, what will the point? What will the saddle point or the point at which we'll have to calculate the value? So Satvika session, if you don't understand what you are doing using partial derivatives, it's completely fine for now because this has not been covered in the lectures. Also, uh, you can try it to do it using the approach which I just described in the fourth question, like just taking these cases and everything. I believe there will be fewer cases in this question. But I would like you guys to like now, since we have discussed a question of this form already, I would like you guys to do this one. So if you can, Arshit is typing in chat the answer, I believe. So Harshit, you made the two equations, right? So you can solve them like directly, like just solving like what you have just written is straightforward, no? Exactly. Like it's uh, a one-line argument after what you have written. So actually, so Satvik or Darshan, you can also try it out, and the answer which you will get here is mm, following the same procedure as the previous question. We get that uh, 1/2, comma 0 will be the so half comma 0 will be the saddle point, and hence C of half comma 0, which will just be equal to like putting x as half and y 0. So if you put y as 0, all of this becomes 0. So this will actually be equal to 4. So this being equal to 4 is the value of the. Maybe I should just highlight the values which we update. 9/5 in the first, 4 in the second. Right. So I hope it is clear to everyone what the value I will be. So yeah. So actually both of these have values and one of these has 9/5 and the other has 4. Okay then. So I hope it's clear to everyone. If it is not, feel free to ask in chat and I'll try to explain again. But other than that, let's move on to the sixth question. Like, so basically, so this is the last question set for the day, like sixth, seventh, and eighth. And I believe like we'll be get over with them fairly soon. So so we are given that consider the following game that two players simultaneously and independently choose a positive integer. The player who chooses the smaller number pays a rupee to the player who chooses the larger number. If the two players choose the same integer, no money exchange occurs. So basically, there are two players, both will choose some integer, and now the one who chooses the larger integer will be the winner. Pretty simple game, right? And we'll have to, the smaller the loser will have to pay 1 rupee to the player to the win. So we are given the question now. So the sixth question says that consider the following two statements. So statement A says that both players have the same set of pure strategies. So what's the set of pure strategies? So pure strategies are basically which do not involve any randomness. So the S1 is the strategy set for player one, S2 denotes the strategy set for player two, and both will be just equal to N. N denotes the set of natural numbers, right? So statement A is this, that the set of pure strategies is just the set of natural numbers for both the players. And second statement is both players have the same set of mixed strategies. So their mixed strategies should also be same, and it's given by this, like x1 comma x2 till like x infinity tuple, where like sum of all these xi values should be equal to 1. And this is the same strategy set for both the players. And now we have to answer like which of these statements are true and which of these are false. So any idea, guys? Like first of all, I hope the game is clear. Like the game is pretty simple that two players just have to choose two positive numbers, and the one who has a larger number will win and will get 1 rupee from the loser. So for sixth question, what will be the answer? Okay, so Harshit is saying that statement A is true. And what about statement B, Harshit? Like will statement B true or okay, so Satvik and Harshit both are saying that statement B will also be true. So good job, guys. So yeah, actually, I think this is a very straightforward question, and yeah, option A is correct, and both statements are true. And like, I don't think it's a lot like it's and much deeper, or it's not very deep to see like why is this true. So two players, both the players have to choose a positive integer, right? And what's a positive integer? Positive integer is just a natural number. So both of these players can only play natural numbers. So that's why their set of pure strategies is just the set of natural numbers. And the set of mixed strategies is basically, so what the players can do is they can play the number I with probability xi, and the sum over all the probabilities should be equal to 1. And so note that since there are like infinite natural numbers, so you'll have to denote it using this infinite tuple, which is like x1 denotes the probability of playing x1, x2 denotes the probability of playing x2, and so on till infinity. And sum of these xk's from 1 to infinity should be equal to 1. And each of these, like since probabilities are always non-negative, so xk should be all greater than equal to 0. And this will be the same strategy set for both the players that both are just choosing. Yes. So yeah, good job, guys. So say option A is correct here. And now we come to like the more interesting question. So uh, what we have to find out is in the seventh question. So we have to find the supremum over the strategy set, like supremum over all the possible strategies of sigma 1. So over all the mixed strategies of player 1, I have to find the supremum. And here I take the infimum over all the strategies of all the mixed strategies of player 2. And the utility function and u of sigma 1 comma sigma 2 is just the utility function of the underlying zero sum game. So what was the utility function? Like if player 1 has a if player 1 wins, like then his utility is +1. If player 2 wins, his utility is +1. And if it's a tie, then both of the utilities are 0. So now we want to find out the supremum. So like I hope everyone knows what is supremum and infimum. So yeah, actually supremum and infimum. So Harshit is asking, is supremum and infimum same as max min? So for infinite sets, Harshita, we like to use the term. So the difference between supremum and infimum is you'll think it's quite small, but in terms of set theory, it is like two different things. So whenever we say max and min, we mean that that value is achieved. But supremum and infimum are somewhat like the values, the maximum value, but which may not be achieved. So for example, suppose consider the function 1 by n, where n is like a natural number. N can be any natural numbers, and consider the function 1 by n. Then what do you say will be the minimum value for this? If a function is 1 by n. Yeah, exactly. So you have written that it will be 0 when n tends to infinity. But note that infinity is not any proper number, right? Infinity is just an abstract concept for us, like that something which is greater than everything. So what we'll essentially say is that so in these kinds of things where we are not so here we are not actually coming to the value zero. The value zero is actually the 1 by n. The number 1 by n does not ever take the value zero, but as n tends to infinity, it goes towards zero. And that's what we say that the infimum is zero. For the function 1 by n, the infimum is zero. We don't say that the minimum is zero. So for normal sets like infimum and minimum are the same, and supremum and maximum are the same for like normal small sets. But when we are talking about infinite sets, like this set where like when n tends to infinity, uh, we are saying that the value zero, it tends to zero, but like exactly zero does not occur at any actual value of n. That's where we say that the infimum is zero. So infimum is somewhat of a lower bound. The infimum refers to somewhat, you can say that's the limit or something like that. Whereas minima and maxima are actually achieved. Like if you say that for a set, the maximum value is like 5, then there will exist an element in the set which is actually equal to 5. But if you say that the supremum is 5, then it does not mean that the value 5 will necessarily exist in the set. It will just mean that every value is less than 5. So does this make sense? What I just described it on a. So Harshit has a question, so you can ask in chat. Okay, so Harshit is saying thumbs up. So it means you understood. Okay, that's nice. So yeah, so there is a slight difference between supremums and maximums and things like that. But for all our purposes, you can kind of think of them as same. But yeah. So what do you, so since like we are talking about like infinite strategies here, so we would like to place supremums and infimums and not maximum and minimums. So, but what do you guys think will be the answer here? Like, so utility function is, as I said, that if one player wins, it's plus the player who wins gets a 1 rupee, so he'll get +1. If he loses, it's -1 for him. So what will be the answer here, guys? Any idea? Any guesses? Okay. So Satvik is guessing that the answer should be 0. Anyone else with any other answer? Okay, so let's see here. Like before coming to the answer, what is this say? What is thing saying? So basically, what you're taking is so right now, like I'll just say like instead of supremum and infimum, I'll just say for convenience as maximum and minimum. Like just for easier understanding for us, I'll refer to infimum as also minima and supremum as maximum. So note that what this says is that so player one first chooses a mixed strategy, and now given player one's mixed strategy, player two will find a strategy such that the this utility function gets minimized. And note that this utility function is basically with respect to player one. Whenever we say that it's a utility function, it's always with respect to player one. So what we are saying here is player one chooses a strategy, and then player two chooses a strategy to minimize this utility function, right? So suppose player one chooses any strategy. So player one will have to choose some strategy, right? So player one will have to choose some strategy, and as soon as player one chooses a strategy, like a player one can have a mixed strategy where it says that okay, maybe assign the for like it can say that assign the probability 1 by n to the first n numbers, or like it can also assign like a probability of maybe like some probability so that the sum over all the probabilities is equal to one, like overall infinite terms is equal to one. So something like maybe uh, yeah. So basically, what I mean is I don't have an example right now in mind, but uh, this player one can always choose some strategy, right? So player one first will have to fix some strategy that is assigns probability pi to the ith number and so on. And then player two gets a choice. So as to minimize the utility. So what player two can do here is just assume so player one assigns like let's say player one assigns probability pi to the ith number, probability pi plus 1 to the I plus 1th number, and so on. Uh, then player 1 sees the probabilities that player 2 sees the probabilities that player 1 has chosen, and it sees okay, so what's the maximum value that the player 1 can choose? Like player 2 can think, oh, that player 1 maybe that player 1 has played like suppose player 1 has only placed probabilities till the first million numbers. Like, so player one has said that give 1 by million probability to the first million numbers or something. So after a million, player one does not assign any probability to the remaining numbers which are greater than a million. Then what can player two say? Player two can just say, oh, that like now it's very easy for me to minimize the function. I'll just put all of the probabilities, like put the probability one for the number 1,000,001. Because now whatever player one chooses out of the first million numbers, the number 1,000,001 will always be greater than the first million numbers, right? So the catch here is so player one first chooses the probabilities. So player one chooses something like let's say whatever it chooses, and we say that the largest non-zero probability whatever player one chooses is let's say a number n. Like n is the small n is the largest number for which player one assigns a non-zero probability. Then player 2 can just choose the number n plus 1 and player 2 will always win, right? Am I making sense, guys? I'm not writing this down in uh, properly here because I think it's more about understanding this than about writing it down. So the order here is first player 1 chooses something and then player 2 chooses something. So player 1, whatever player 1 chooses, player 2 knows what this player has chosen. So player 2 will just choose something which is greater than whatever player 1 has chosen. And so player 2 can always make this utility function equal to -1. Like player 2 can always make player 1 lose. Harshit, Satvik, am I making sense? Okay, it makes sense to you guys. That's nice. So yeah, so the crucial idea, so like it might seem that oh the game will be like the this value should be zero as Satvik guessed in the chat because like why would you differentiate like both the players are choosing some numbers and so why would you differentiate that what the one player's utility will be and what other player's utility will be? But note that the difference here is in the order of the choosing. That basically player one is essentially choosing first, essentially choosing a number first. Whereas after seeing all these, like whatever player one has chosen, like player two sees whatever player one has chosen, and now player two can just choose something which is greater than what player one has chosen, right? And so player two will always win, and player one will lose. So this utility for player one will always be -1. Like it's supremum because we have an infinite series, so it will be actually in the limit it will be equal to -1. But let's just ignore that for now because it will become more about mathematics rather than the underlying game theoretic concept. So -1 is the answer here. As player 2 can always choose a number larger than whatever player 1 has chosen. Making rules. What am I writing? Yeah. Right. So whatever player 1 chooses, player 2 can always make him lose. And since we are so always this infimum will come out to be -1. And now we are taking the supremum over all values. So we are taking maximum over all the -1s. But maximum, if all the values are -1, their maximum will also be a -1. So that's why this will be a -1. Now let's move on to the eighth question. I hope like eighth question is again in the same spirit. So what do you guys think will be the answer to this now? So first we are taking, so this was like max min and now we are taking min max. That player two first player two is the one who's choosing, and then player one chooses something to maximize the function. So whatever is chosen by the player two, and now we need to maximize this utility function. So can I say that the player one can always choose something which is greater than whatever player two chose here? Okay, so Satvik has written in the chat that the answer is one. So good job, Satvik. Like, that actually is the correct answer. Harsh has also written one, so that's nice, guys. So it means that you guys have got the correct idea for how to approach this question. So again, maybe just to reiterate for like everyone who will be watching on YouTube also. So this supremum is, so first here the player two is choosing something, right? And now is the turn of player one to choose something, and player one can maybe since it wants to maximize this utility function, so player one will choose something which is uh, essentially greater than whatever player two chose. And so player one can always maximize this utility function to one because player one can always make himself win. Whatever player two chooses, player one will choose something which is greater than that. And so player one will always win. So this supremum comes out to be one. And now we are taking infimum over all possible strategies. And so and so all of these are ones. So we are taking minimum over ones. All of things are ones. And so minimum over plus ones will just be a +1. So yeah, maybe I'll just copy this and so the answer will be 1 as player 1 can always choose a number larger than whatever player 2 has chosen. And yeah, Like, I hope this kind of explanation makes sense. Like, why I'm saying like player one can always choose a number larger than player two plays, because here player two is playing first and then player one is playing. Here I'm saying that player two can always choose a number larger than whatever player one plays, because first player one is playing. So it might confuse you. Like, one time I'm saying that player two is choosing the number uh, after player one plays, and in the second time, player one is choosing a number after player two plays. This is because, like, in the first case, we are first allowing the player one to choose and then player two to choose. In the second case, we are first allowing player two to choose and then player one to choose. And so, like, this will make a difference. In this case, we'll get answers -1, and in the second case, we'll get answers. Okay, then I guess this is all I had for the day. Yeah, and we are just on time also. Like, it's the session, only 5 minutes more are left. Okay, so I guess I'm done for the day from my side. So if there are any doubts, guys, there are 5 minutes remaining. You can ask if you have any doubts in any of the questions we discussed or anything. So Harshit was typing something in the chat. Is there something that you wish to ask, Harshit? Oh, okay, so you're okay. I guess since Satvik and Harshit, none of you have any questions to ask, then I guess okay. Satvik is asking, can we get resources for practicing such questions? Uh, I don't know. So, Satvik, I posted, maybe I can just copy and paste that link again. But in the chat, I put out some resources which have been shared on the NPTEL page, the books which the professor is following. Like, I'll just copy and paste the message again. So these books, like this Game Theory and Analysis of Conflict by Meyerson, this Dynamic Non-Cooperative Game Theory by Baser and Olser, and similarly these 2-3 books also. So all of these books contain the topics which we are discussing. So in these books also there are practice exercises, right? So you can definitely practice these kinds of questions from these books. And like also, like, if you're not able to understand some theory from the lectures, you can uh, try to understand them from these books also. So yeah. Okay, then I think there are no, I don't think any of you has any other doubts left. So thanks a lot for joining, guys. Hopefully, I'll see you guys again in the next week session. Same timings, Monday 6 to 8 p.m. So till then, I guess, goodbye and take care, guys. I'll be like stopping the recording and you can leave the session if you wish. Thanks for joining the session, guys. Bye bye.